Hello. In previous weeks, we have discussed three methods for extracting estimators for the parameters of random variables. These methods are the method of moments, least squares, and maximum likelihood. The quiz that followed the video on the expectation and variance of the normal random variable showed you how to apply least squares and the method of moments to get estimators for the parameters of a normal distribution. In this video and quiz, we are going to thus consider how to apply likelihood maximization for the same tasks, namely to get estimators for the parameters of a normal random variable. As you hopefully remember from when we first covered this topic a few weeks ago, in likelihood maximization, we note that the following product is a measure for the probability of observing the results that we did. In this expression, the small xi are the results we got when we generated our n independent and identical random variables. In this case, we will assume that the random variables we are generating are all normal random variables. The probability that we will use in this expression is thus the probability density function for a normal random variable. We can thus write the following expression for the likelihood of observing the particular set of results, the xi values, that we did in the experiments. Notice that the likelihood here is a function of the parameters of the distribution, namely mu and sigma. Further note that if the values of these parameters were set so that the likelihood was small, saying our results were samples from this distribution would not make a terrific amount of sense, as we would essentially be saying that the results that we obtained were very likely to have been generated by this particular distribution. This way of thinking thus led us to conclude that we should find these parameters by maximizing the value of this likelihood. As we found when we last applied this technique, it is often easier to maximize the logarithm of the likelihood rather than the likelihood itself. The location of the maximum in the function is the same as the location of the maximum in the logarithm of the function. So simplifying this function in this way is fine and also advisable, especially if it makes the problem easier. We will thus take the logarithm here and arrive at the expression that is shown on the slide for the log likelihood. To find the maximum, we need to differentiate this expression with respect to the parameter. In this case, we're going to differentiate with respect to the parameter mu. When we do so, we find that this derivative is equal to the expression shown here. Notice that we can write the sum over all xi as n multiplied by the sample mean, as shown here. And that if we add n copies of mu together, as we are doing in the sum in the center part of this expression, we get n multiplied by mu. Finally, notice that because we are at a maximum, this first derivative must be equal to 0. To satisfy the equality here, we must therefore have that the sample mean is a suitable estimator for mu. Now, as we saw in the last video on the topic of maximum likelihood, we must check that the estimator we have arrived at is unbiased, and we must also determine the asymptotic variance before we use these estimators. Checking for bias in this case is straightforward. We know that the sample mean is an estimator for the expectation of the underlying random variable. Furthermore, we know that the expectation of a normal random variable is equal to mu. The least squares estimator that we have arrived at is thus clearly unbiased. For the asymptotic variance, we use the expression shown at the top of this slide. We can recall from our previous slide that the first derivative of the logarithm of the likelihood is given by the following expression. The second derivative is thus n minus n divided by sigma squared. There is nothing random in this expression, so we can insert it directly in for the expectation here. We thus arrive at the expression for the asymptotic variance shown here, namely that the asymptotic variance is sigma squared divided by n. This result shouldn't really surprise us, as this is just the variance of a sample mean computed from n random variables. This is a formula that we have seen multiple times in this course. I hope that is reasonably clear. In the quiz that follows, you have the opportunity to apply the same logic to calculate the maximum likelihood estimator for the parameter sigma. Good luck, and thanks for your attention.